Okay. Go back to sharing. Okay, perfect. So today we will deal with model theory control. So control means that we are going to not evaluate a given policy, but we are going to try to find an optimal policy. And model free is because we will not have access to all the details of the model, but we will only have access to it indirectly through trajectories. The lecture more or less is divided in two. For the first part, I will build upon the past exercise, so on value evaluation. We will see how value evaluation works on the Q value function, and then we will use this to build two methods, which are very similar, but have important differences between them. And one is Q learning. The first, actually, the first one we will deal is SARSA, and then Q learning. Then most probably, then 1 hour will have gone past. So after the break, we will deal something slightly more advanced than SARSA, which is expected SARSA, which in a sense connect both Q learning and SARSA. And then we will deal with just briefly on a topic which you have seen in the classes, in the theory classes. And it's always a nice thing to have as a tool, which is a bit of convergence discussion about the learning rates, and you will see epsilon greedy epsilon, how to change epsilon in time. So let's start for real. Okay, Q value learning. Last time we have dealt with many ways to evaluate the value function, the state value function, so V of S, given a policy. Right now we will construct on them, but we want to, in our main focus, we will be the control, so the finding of the optimal policy. But notice I apologize for the inconvenience again, but now I'm switched back to the correct notation, in the sense the notation which is most common, which is now the rewards have the time after the action. So this is just a side note. Okay, for these algorithms of control, it will be more convenient to use the Q value, so the state action pair value, and not the state value. So we will first see the definition again of this value function, and then Q. So the definition of the value function for the state action pair is just the expected value.
We lost you. I think we lost you a little bit. I don't know if everything or only me, everybody or only me, but I didn't hear you for a little while.
Okay. So
the definition from the definition.
Okay, perfect. Let's go back to the definition. So essentially, the first definition of a value function is basically identical to that of a state function, but so it's just the expected value of the sum of all the future reward discounted, starting from the position S, so from the state S. But now, instead of always following the policy, the first action is taken, and it's exactly that of which we are evaluating. So the Q value for a state and action is I am in the state. I'm doing that action first, regarding what my real policy is, and then afterwards, and only afterwards, I will follow a policy. So basically, it's the same as the value, but the first action is taken. As always, there are many equivalent formulations for this value function, and one, for example, is just that the value function. If you think about trajectories is the expectation value of the first reward plus I'm discounted the value of where I end up. So I'm in a state S0, I do an action A0, and then I will be in some state S1, and from there on, I know that the expected infinite future reward discounted is just the value of that state. So I can rewrite it as the first reward plus discounted value onwards. Then another formulation could be which connects only Q value function with Q value function is just that I'm in a state, I do an action, and I get a reward plus from that state, from state S1, I'm just doing all actions which are available with the probability given by the policy, and I'm evaluating the value function for the pair, for all the pair new state and possible action. So which is just what it's written here. So I'm summing over all possible actions on the new state for the probability of taking that action, which is just the policy in that state, and the value of being in that state and doing that action. So as always, we will have different formulation which are equivalent, but will be more useful in one or another case. So first thing I wanted to do to bridge last lecture with this lecture is just do pure value evaluation. So I will give a fixed policy. I will not try to optimize it. I will give a fixed policy and I want to evaluate it, but I want to evaluate it as a Q function. And I will use the third formulation, which connects the value function for each for a state and action with all the value functions for the new state and all possible value actions there. So this is just the class. You will see that it's the same structure as the last lecture. I have tried to maintain the same structures of all the main, let's say, code parts. So it's easier to go back from one to another. So this is the Q evaluation. And again, what I want is just I'm asking for the gamma for the discount factor. I'm asking for the system size. Now, while the value had the same size as the state, now we have a size which is the state multiplied by the action. So I need have to have both the space size and also the action size of the space. I'm getting the policy because I'm trying to evaluate the policy. So I'm asking that from input. Again, there is the learning rate as always. Now I'm defining this a zero vector, zero matrix with this is just a fancy notation to say that the size is the size of the space and of action altogether. And again, this is the most important part, which is the single step update. So remember what we are trying to do. We are trying to get the old evaluation of Q, and I want to do the new one. And in TD0, if you remember, if okay, to the function, I'm just getting the state, the action. So this was like S0, H0, R1, and then the new state S1. This is what we give to the algorithm the last time. And if you remember, as in the last time, if the episode was finished, then in for example, temporal difference 0, we had that the delta was the reward plus 0 minus the value in the state. We have the same thing, but instead of I call it delta Q to differentiate it, and I have reward plus 0 minus the value, the value of the pair state and action. Okay, so basically you see that in a sense it's identical. Instead of having the value only for the state, I have for the pair state action. And then if the episode is not done, so if I am in a new state from which I can do actions, if you remember in TD0, I had the delta was the reward plus the discounted value of the new state minus the value of an old state. And here what I have is the reward plus the discounted. And now instead of having only a value in one state, I have to sum up for all possible actions and the value of the new state for all possible actions. This is exactly what is written here. I'm in a new state and I have the sum of all possible action in the new state, which in Python is just done with a dot product between the Q values in the new state and the policy I have there. So this is the policy, so the probability for all the action there. This is the values for all the state action couples. And then I minus self Q values for that, for the old state, the old action. So you can see the parallel between them. And as always, I'm asking also, since I want to do trajectories, I'm also added a function which it says, okay, give me an action following the probability if I have the policy, if I give you a state, which is just a random choice of the indexed actions, while the policy is that of the state. Okay. Okay, so this was just, it's a bridge between value evaluation with V and value evaluation with Q. I thought it would be useful to have it as a first input. What are we going to solve today with model field control? Grid word. It's a grid word again, so it's a squared word in which you can move up, down, left, right. It's a bit different from the other one, but basically it's the same. There are transition, again, you can move left, right, up, down. You cannot move outside of a box, so you will say put. It's deterministic in the sense that there is no random probability that you do strange things. If you do an action, you will end always in the same spot. If you try to go out or do impossible thing, you will be stuck there. Now we added a cliff, so you will see then we have a region in which if you go there, you fall down, and you are immediately transported to the start. So also the start is a new thing. We always start all the episodes in a single point. We try to move. If you go out of the cliff, you go back to the start, and the episode ends only if you are at some point, which is the end point. Okay, I'm creating the word, which is like this. So you can see it's basically a rectangular word. We will start in the left bottom corner, and we will end in the right bottom corner. All move actions cost 1, but if you fall from the cliff, you break your legs, it costs 100, and you start from the beginning. Okay, so do not fall from the cliff. It's the main message of today's lecture. Again, to make a parallel with last lecture, I tried to create a class of the environment, because this is the general gist of how environments are done, like in OpenIE gym. So it's a very simple one. You have an init function which just says, okay, create an environment. It asks for a word, and it asks for the start and the end. Okay, so good. The shape is basically it's a very simple shape as this. The start position and the end position are given in the beginning, and you have a value which just remembers the start value, and of course you have a variable which says, okay, the episode is done or not. You have a reset function, as always in this environment, which just go back to the start and put the episode done to false. And you have just a step function with an action which takes the current state and tries to do a new action, and it tries to do a new position. And as I said, all moves cost 1. But if you fall off of a square, you stay put. So you go back to the new state, actually goes back to the old state. And if the word in that position is as a minus, so you are in the cliff, then you go back to the start, and you get the very negative reward, which is the value which I put in the cliff, which is -100. And it just saves in the memory the position. Okay, so this I will. Okay. To beginning, as we said, we did not do any control. We want just to value evaluation. So what policy we want to evaluate? I just put a random policy which is equal to all places. So it's a policy which is whichever is the state is, always that tries to do the same thing. It will never go to at the end, I changed it a bit. I apologize. This is the actual policy I'm using. We can just write to 0.2. And okay, let's just look at it here. Basically, this is the policy for each state. I'm moving down with a probability of 0.2. I'm moving up with a probability of 0.3. I'm moving right with a probability of 0.45. I'm moving left with probability 0.05. Okay, just the policy I put. Then I create the environment. I create the gamma and the learning rate. And what I'm trying to do now, clearly I forgot to, I apologize. Okay, it takes a bit. Okay, so what you see now, it has ended the episodes. Now we did the trajectories. So we did 100 episodes. We initialized our evaluator. We are going through 100 episodes. Every time we start from the start, which is bottom left, and we take the state, we take the action, we see which action, so up, down, left, right, correspond to the index of the action we took. And until the episode is done, I'm just doing new state, I get the reward, I'm evaluating I'm giving the state, the action, the reward, the new state to the evaluator, and so on and so forth. At the end of all, I've accumulated the values, the Q values inside of the class, and I'm asking for them. So this is just now in Q values, I do have the Q values evaluated for that single policy for that word. Now we can watch them. So these are the Q values for being in a state on the right, for being in a state and doing the action down. So you can see that if you are just above the endpoint, so here, the value is -1, which makes perfectly sense, because if you are there and you go down, it costs 1 because you move, but you have ended. So that is the most, like the easiest thing to understand. Then if you are close to the cliff and you go down, you will see that the numbers are extremely negative, because of course, for sure you will pay 100. Then the numbers are not perfectly, I mean, they are not converged yet, but it's clear that if you're there, you're doing a down action, it's a bad thing. If you do an up action, you can see that basically they are negative, but not incredibly so, because it means that essentially you will never have a probability of going to a cliff. Then if you are going right, again, it's not that bad. And if you are going left also, it's not that bad. Okay, so these are not converged, but just to present what it does usually. So you will have, instead of having only one map of value function, one for each state, you will have as many maps as many action you can take. So if you want to know the value in that position, you actually have to compare all four action maps. This was just that we have done basically what we have done in last lecture, but with Q. This was just what I wanted to show you. Now let's go to the new part. We're going to do control. So we want to find the optimal policy. This is the most important thing. Why do we use a Q value instead of a V value? Because now with a Q value, it's very simple to find the best action, in the sense that if I had the optimal value Q star of being in a state of doing an action, the optimal policy is trivial. Okay, the optimal policy is just that policy which does the best. So you take all the possible pairs state action, and you take the one with a higher value, which is defined as here. And okay, so the optimal policy is just the action that maximizes the state action value. So this is a very simple thing to ask. If you had all the proper Q, this is a very simple to ask. Okay, I know that I have for action which has the largest value, do that. This is why one use the Q value function. But of course, we do not have the optimal value Q star. Otherwise, why are we even talking? We have to find it, and we will find it iteratively. And all the different algorithms are basically functioning the same way. So it's an iteratively process of prediction of the Q and making a better policy, better prediction, better evaluation of the Q, better policy, better. Okay. So it's iteratively. We do a random guess at the beginning of the Q. We create a policy with some properties using that Q. Then we create a new estimation of the Q using that policy, and then a new policy with that Q, and so on and so forth. Okay, and at the end, hopefully, what we have as the nth estimation of Q will be a good approximation of the optimal value of Q star. And then the policy, we can ask for a greedy policy. So we can ask for a argmax, so the best action to do following that approximation, and that will be our approximation of the optimal policy. As I said, all algorithms follow the same principle, but they will be slightly different in how to estimate the Q star function. Why are we doing this? Why is it not a trivial task? It's because of the delicate balance between exploration and exploitation, which is something you also have seen in class. The idea is that now we want to exploit our knowledge to find a good action to do, but we want also to do action which we do not think that they are good, because we want to still gather more information on the world, which at the beginning we have no information on the world. So what the policies we want to use to create trajectory need to balance two different drives. One is exploitation. Exploitation means using our current information to do the best action possible. And in particular, exploitation means to be greedy, means that if I have an estimation qt at time t of in the state st, being greedy means I will do what is the best thing to do given that estimation. Clearly, this is not a stupid thing to increase the future reward. You get good reward, but the problem is that the current information could be wrong or incomplete. So in the end, you will be for sure, not for sure, but I mean, it's very high chance that you're not do it optimally. Exploration is the other thing, which means that you will do actions, and you even think that you are doing actions which are poor, which are suboptimal, but the possibility is that this could lead to a larger information gain, and this eventually will lead to better rewards than experience so far. Okay. Of course, if you already had perfect information, all you do with exploration is waste time. Okay. So there is a very simple way to understand this with ice creams, and it's that exploitations. So let's think you have never tasted any ice cream except for watermelon and lemon, and you decide that watermelon is better than lemon, and you say, okay, from now on until I die, I will only get ice cream to watermelon. Okay. I don't care that there are many other. I know that I prefer watermelon to lemon, so I don't want to make any mistake. I will only take watermelon. This is clearly the worst idea of your life. But on the other point, exploration is like, okay, I know that I love chocolate. I always love chocolate. Chocolate is the best thing ever. But since I'm not entirely sure that chocolate is like the real best, every time I go to an ice cream, I never take chocolate. I take a different flavor. So you, at the end, you will have nuts, melon, mint, strawberry, puffo. Once I had gorgonzola and nuts. Okay, but the problem is that at the end you may find out that actually you prefer chocolate all along. Okay, so balance these two things. A simple way to balance these two things with you saw, which is very common, is called epsilon greedy, which means essentially you take a probability epsilon, which should be rather small, and with probability 1 minus epsilon, your action is greedy. So it means that you're doing what you think is best with respect to the current information. But with probability epsilon, you're doing pure exploration. So you do a random action between all possible random. Okay, so the probability, the policy epsilon in a state is with probability 1 minus epsilon above. It's like the action which maximizes the Q value for the pair state action. And with probability epsilon, it's any action at all. Okay. Epsilon greedy policies are very well known and studied. The problem is that if you have a constant epsilon, it means that you, even at convergence, even when everything is known, you will still have an epsilon probability of doing to work suboptimally, which is a lot, which means that your regret grows with time, grows linearly with time. So it's not the best thing to do, but it's the best thing at least to start. Okay, that said, let's go to the technical part of our first algorithm, which is called SARSA. SARSA is what is called a non-policy TD control method. It's very straightforward. We said that all these algorithms had two elements. One element is a way to update the estimation of a Q value from one step to another. And the other part of this algorithm is a way to construct a policy. So the way to update the current estimation will be done with the time difference error in Q. So we will have, we will see how we define it, but we will have an error, time difference error in the Q value. And each step we will see that the new estimation of Q is equal to the old estimation of Q plus a small part of the of this error, which we have just calculated with one step. And then using this evaluator Q, we will have we can construct an epsilon greedy policy, which of course will be different at each step because the QT will be different at each step. And again, we will use what we defined before as an epsilon step. So the two ingredients of the SARSA is that my update of evaluation is done with a time difference error in the Q value, and my policy, but as a policy, I just take epsilon as epsilon greedy. What does SARSA need to work? At each step, it needs the state where I started from, the action I took, the new reward I gain while I was in the new state, and also the next action I took, because I want to compare state action pair. So instead of the normal TD0 with, so last time, we also need the new action. And if you put SARSA together, it's SARSA, which is the name of the thing. And the update is calculated as the temporal difference error TD0, and it's just this one. So you can see that delta Q is equal to the reward I got plus the discounted Q value for the new state and the new action which I took, because this is the action which I took, minus the Q value of the state where I was and the action I took before. Okay, so differently from before, before I do this update, I also need to take a new action, okay? I need also to be in a new state and take the new action. This is similar to, for example, what we did in the V value evaluation with T0, which was the R plus gamma V minus V. And this, instead of having the V in the new state and V in old state, we have the state action pair new and the state action pair old. Okay, but there is this parallel. And the update is just as written before. So a second convergence caveat, which is, before we said, okay, if you do a constant epsilon, it's suboptimal, especially a long time. If you do a constant alpha, you will never converge. You will fluctuate around the true value. And as you've seen in class, actually there are, for example, two criterions which ensure that the value goes to the optimal value with probability 1 with infinite time, which is that the sum of the squared of the terms should converge, but the sum of the terms of the learning rates in time should diverge. Okay. This is the pseudocode, which will now translate into a code, which is very similar to what we have done before with evaluation, but we will have a one step further with the policy. You have to you have some algorithm parameters which are the learning rate and the epsilon for the policy and the learning rate for the update. You initialize Q, we initialize Q to 0, and we also remember that the Q of the value of the terminal state is 0 and will stay 0 forever. And then you do episodes, and for each episode you start with a state S. You choose an action. You take that action and you have a reward and the new state. And then you choose an action again, also in the new state before doing the update. And then you do the update. And the update is just that you take the Q value and you sum the delta Q of it. Okay. And then you start again. You already took the action, so you go in the next state, you take the action, and so forth and so on. Okay. Where this seems that there is only prediction. No, there is also the fact that the policy is improved, because you see now we have epsilon greedy, and these epsilon greedy are constructed using the current Q. Okay, so the prediction, so the better estimation is done in this line, updating the Q, but the actually control, so getting policy which are better and better, is done because the epsilon greedy changes as a function of time, because it depends on the current estimation of Q. Good. So now let's go to the code. This is a very simple Python code. I create a control, SARSA control class. Again, I just need a gamma. I just need the size of the system, because I need to initiate the Q values. I need the learning rate. I need just to create a zero matrix of the size of the state multiplied by the actions. And then, as always, I have one simple part with algorithm, which is the single step update. Now I need state, action, reward, new state, new action. And what it does, and it does mostly the same thing as before, with a slight change, in the sense that if the episode is done, again, as in TD0, I just take the new reward, 0 minus the values of the state action pair I was in. But if the episode is not done, I do the R plus the discounted Q value, and this is not a Q value all possible action. No, it's the Q value of the new state and the new action, minus the Q value of the old state and old action. And then the update is essentially the same as before. I'm just adding a small percent of this delta Q error. If I want to get an epsilon greedy policy, I'm just adding it as a function. Sorry. What it does, I'm asking for a random number from 0 to 1. If this random number is smaller than probability epsilon, do whatever you want. So it creates the probability of actions, which is flat over all the action space. If not, then I have to find first what is the best value, which is this. The best value is the maximum value for the Q values for that state. Now, since Python returns only the first one, but we want to share the action in all possible actions which are the same, I added the second part, which is a mask, which says that the best actions, which may be one or maybe more, is just all the possible actions which share the best value. So I take the Q values in that state. So it's a Q value array for all actions. And if any of those is equal to the best, for sure one is because I took it as that, but it could be more, then the best action is just a mask which says you are not, you are, you're not, you're not. Okay. And then the probability of action is just it's a mask again, but now it converts in floats. It's 0 if you were not the best value, and 1 over the number of best action if you are. Okay, so essentially this is it's a simple thing. Instead of doing I want the best action, I am asking what is the best value? How many of you have the best value? Okay, the probability of among you is uniform. Okay, but the main point is if you have I have epsilon probability of doing anything, you have 1 minus epsilon probability of doing an action which is the best of one of the best if there is a tie between them. And then using these probabilities, I'm just taking an action. Okay. Then I can also ask, okay, this was an epsilon greedy. What is the greedy policy? The greedy policy is just doing this. So I'm asking for the argmax for that Q value in that state. Notice that again, this is technically wrong in the sense that I should ask for again splitting the probability of ties. I do not care because right now the greedy policy means that I just finished, so I'm fine with only one of the possible greedy policy. If I wanted to keep on learning, I need some exploration, so it was actually much better to have this splitting. Okay, so notice that here there is this slightly incongruence if you want, but the greedy policy is defined as this. Okay, let's do control. And then maybe we can take a break or see how it is. We're doing 2,000 episodes, so we need a larger number of episodes. We initialize the SARSA with some learning rate, some epsilon, and now we also keep track of the performance. So for each episode, I'm how many steps or what is the reward, the final reward of the episode. And then I do a run over the episodes, and as always I'm doing the same thing, but now the only difference is that I have for the state, then the action, and this is because the action from the SARSA is just 0, 1, 2, 3, and the action is as a vector is like the arrow of direction. Okay, so this is a map between 0, 1, 2, 3 to move left, move right, move up, move down. If it's not done, then so this does a whole episode and takes the new states are done and it acts. Then I save the performance. So I save the reward in the performance. I get the new action, and only then I do the single step update. So you can do the single step update with the state, action, new reward, new state, new action, and then back and back. Okay. So first of all, I need to, I always forget, and I apologize. Okay, it's calculating, good. So it calculates. So 2,000 episodes maybe was an incredibly stupid idea with Zoom on. No, okay, good. Okay, now you can see again, this is what happens. So the Q values for action down are as such. The Q values for action 1 are such. The Q value for action right and Q values for action left. So again, you cannot see only one map of value, but you have as many maps as. But the most important thing I wanted to show you is this. Okay, so this is now this is the word above. This is the best Q for each state, the best value. So I'm already doing the max over the actions, and here you can say the action, and the action actually says, if I start here, I have first to go up, then to go right, and then to go down. Okay, and this is what Sarsa learns. And now something should be slightly off for you, because I said before that here rewards were movement were deterministic. So if you decide to go close to the cliff, actually, if you decide correctly to go all the way right to the cliff, you should not be able to fall off. So instead, Sarsa does this thing, which goes first up, then right, and then goes down. And now, maybe before closing to the break, we can discuss why is it. And the reason why is it's because Sarsa is an own policy method, and so it means that it's doing the trajectory, so it's following the trajectories with a policy, and it's evaluating the same policy which it's following. So we are not actually we are trying to get the best epsilon greedy policy possible, but we are still evaluating that epsilon greedy policy. And epsilon greedy, what it does, it has a epsilon chance of doing a random choice. So actually, Sarsa says that in the world of epsilon greedy policy, since you have an epsilon probability of doing things randomly, you should not ever go close to a cliff. You should go up, right, and down. Why? Because I'm learning the values for the policy I'm following, and my policy I'm following is actually dangerous close to the cliff. And here you can see that epsilon greedy function, while they are a good tool because they give a balance between exploitation and evaluation and exploration, actually with Sarsa as a double edge, because then you are optimizing that kind of policy, and that kind of policy can lead to Q value which are not exactly what you want. So with that, perhaps we do 10 minutes of break, and then we see something which is slightly different. So it's an off policy, so where the policy I'm following and the policy I'm evaluating are two different things with Q learning. And then if we have time, I hope so, we will do expected Sarsa and a bit of convergence. Okay, so I can, I apologize, there were, yes, exactly. Now we are doing epsilon, which is finite. At the end, we will see that we are actually taking epsilon and we are changing in time, and we will see that it will converge. So epsilon greedy with constant value are suboptimal, and that can be suboptimal in a very visible sense as here, but clearly there is a way to change them on time, which again is proven to be optimal. Okay, let's stop. Pause the recording. Please resume the recording.
It's recording now.
Perfect, many thanks. Okay, so far we've seen that we went into the Q value. We saw how to evaluate the Q value given a fixed policy. We saw the first method, which was Sarsa, which was iteratively evaluating Q with a time TD error, delta Q, and then it was choosing a epsilon greedy function to explore and exploit, and so forth and so forth. And we saw that it's a good way, so it learns in a reasonable way to go from the start bottom left to the end bottom right. It's a special, at least with an epsilon which is fixed, it's not optimal, but it's still a good solution. It's not doing random things. Now we are going to the second of this very simple class of algorithm, which is called Q-learning, which is off policy. So again, it's very simple. It has a policy which you use to explore, which is again the same as before. It's epsilon greedy, and exploration means that with epsilon greedy, we recall it's just that with as a probability epsilon, which if with probability epsilon do a random action between all it can, with probability 1 minus epsilon it does greedy, so it does the best action with the current evaluation of Q. So what is different? Many things are similar to SARSA in the sense that at every step t, we store the old state st, we store the old action at, we store the new reward rt plus 1, the new state.
We can't see your screen, by the way.
Ah, yes, that is very simply because I forgot to share. Okay, thank you very much. Fortunately, I was just reiterating stuff. So we are now Q-learning. And the idea is that, again, we explore using an epsilon greedy function, which is the same as defined before. And many things are the same as in SARSA. So with every step, we have old st, old at, new reward rt plus 1, new state st plus 1. Then we do not need to take the new action, because what Q-learning does is that the new value of the Q value, which it does for the TD error, is using the best action, using virtually, of course, the best action available for that state. So instead of being QDT of ST plus 1 action a t plus 1, so the action it takes, the action in the trajectory, it does something which is separate from the trajectory, and it considers the value which is the best possible value given the estimation QT. Okay, so the only difference with SARSA, which is a large difference, is that update of Q is done with this term here. Why is it off policy then? Because we have a mental separation between the trajectories, which are done following epsilon greedy. So in the trajectories, at least epsilon, in epsilon percentage of the action, you are doing random things. You are doing non-argmax over action. But in evaluation, actually, you are only evaluating the new state pair, which is not done with a probability state action, but it's done using the argmax. So in a sense, it's more like evaluating something which is closer to a greedy, but exploring with an epsilon greedy. So there's a shift between what it's evaluating and what is using for exploration. The two policies are not the same. Okay, this is what it means with off policy. The algorithm, the parameters is as before. You have a small learning rate, a small epsilon. You have, wait, I wanted to, let me, sorry, let me have this here. Okay. You initialize your state, you're taking an action from the policy which is epsilon greedy. So this is the policy you're actually using to explore, which is the epsilon greedy. Then you take the action, you observe a new reward, then you observe a new state. But the update is not done with the probability given by the policy you are actually following, but it's done using this greedy choice of action. Okay, so the value is updated with max over action, which is a greedy conception of the policy you are evaluating. So the policy you are evaluating and the policy you are following are two different things. And then you do it over and over for many episodes until the end. Okay. Why is it off policy? Again, I said it, but it's very important because before in SARSA, you were using the update in the queue using the new trajectory state ST+1, AT+1. So you were evaluating the policy you were following. Here you are evaluating a policy which is not exactly what you are following, because you are following an epsilon greedy and you are basically evaluating a greedy. But as always, the difference in now the host is me again. good to know. Again, the structure of the algorithm is basically very similar as before. Again, it just needs the gamma, it needs the space, it needs the learning rate, it needs to initialize the Q values, initialize to 0, but it could be initialized to other things. There is also a discussion about the optimistic evaluation, etc., etc. I do the most basic thing, initialize everything to 0. The single update is again extremely similar to SARSA. I do not need the new A, so I do not require as input the new action. What I do is, if the episode has ended, I just do the reward I took plus 0 minus the Q value for the pair state action. If the episode has not ended, I have to find the best Q value available at the new state. So I go to the new state, I look at the Q values in that new state, which is an array for all action, and I took the best. I do not take the one I will follow in the trajectory, I take the best. And then the delta Q is just reward plus gamma, so the discounted best over the new action available minus the old Q value. And the update is exactly the same as before. So you see the structure is the same as before. This 2 line of code changes from being an on policy SARSA to an off policy Q-learning. Again, if you want an epsilon greedy policy making, you have to ask for a state, you have to ask for an epsilon, and this is the same as before. Probability epsilon, do whatever you want randomly. Probability 1 minus epsilon, find the best value, find all the action which share this best value, and then do a flat probability of a reaction which have the same best value. And then do a random choice in this probability, which is either completely flat or it's flat only for the best action. Again, I define for convenience the greedy policy, which means that once you have the Q values, once you want to say, okay, I just want to know what you arrived so far as a greedy policy, you will get it. And then I have to compile it, otherwise I will, as many times I will do wrong. What I do now is the same I did before. So I am trying to make a Q learning control, 2000 episodes. I'm just initializing this new algorithm here. I'm just taking track of the performance. I'm just running over the episodes. Every time I'm resetting the episode, every time I start with a current state, I do an action, go on, and then until the action episode is finished, I just take a new state, the new reward. Am I done doing the environment step? Keeping track of the performance, taking the new action, looking what exactly the new action is in left, right, doing the single step update. Now it's not SARSA anymore, but it's SARS, because it does not require the new action in the trajectory, because it takes the maximum possible overall possible action it has. Okay. Then again, I'm asking what are the Q values you arrive to, and then you can see that here, this is actually similar to before, but with two main differences. The first one you can already see visually, which seems that there is much less variance here. Okay, here there is more variance. Okay, so you can see that it does not seem to be a constant gradient and everything. Here it seems to be more well behaved. And also you can see that something which is very cool. Okay, you can see. Let's see this. Okay, you can see that actually has learned the already learned the optimal policy, and you also can also see that the value for the optimal policy is just -1, -2, -3 here. Okay, this has not converged perfectly, but the policy has. But in any case, you can, at least for some of the trajectory, they are correctly the value is correctly describing the distance between the endpoint. Okay, now something which can be a bit counterintuitive, and it's coming from the fact that you have an on policy and an off policy. So remember, SARSA did not find the optimal policy, but it was a known policy. So it was evaluating for the policy it was following. Q-learning found the best optimal function trajectory, but it actually was following a different one. What have I done? Oops. Please. Okay, I hope you're not hearing what I'm hearing. Okay, so what is this? This is just what I stored, so the trajectory, the performance in time. So orange is SARSA and blue is Q-learning. And what you can see two things. SARSA is much more consistent towards a higher value, but it never reaches the highest value which Q-learning does. But Q-learning actually has a much worse performance during the running time. Why so? Because both are actually following epsilon greedy policies. So both of them sometimes do random action, and sometimes those random action go to the cliff. SARSA has learned to optimize an epsilon greedy, so it has learned to optimize that policy so that to minimize those actions, those falling in the cliff during the trajectories. Q-learning has used those trajectories and using those trajectories to optimize and find the best policy, which is separate to it. So Q-learning has a much worse performance because it is following trajectories which follow the cliff, but do not care about those which follow the cliff because it knows that actually you could not following over the cliff, so he actually learned to go over the cliff. Okay, in a sense, the best performance of Q-learning is better because he has found with probability y minus epsilon a better optimal policy, but since they are both following, so the trajectories are given by the epsilon greedy policy, SARSA is doing better because he has optimized itself for the fact that you have an epsilon probability of doing random stuff. This is just to see the main difference between them. SARSA on policy, Q-learning off policy. Okay, let's do one more step to expected SARSA. Again, new word, but actually 2 lines of code. Expected SARSA is a very simple modification to a SARSA. It's helpful because it reduces some of the variance of SARSA, because SARSA, if you think about it, needs every time you have to have pairs of state actions. So if the action space is very large, then every time if you are in a state S prime, you need to all the time, I mean, you have too many trajectories to check all the possible actions. So a way to remove that, to say, wait, if I am in a new state ST plus prime, I'm not asking for my trajectory where I'm going. I'm not trying to find as the Q-learning the best thing I can do, but I will try to find the expected Q value following the policy I'm actually following. Okay, it's a bit complicated, but it's actually the only difference with SARSA and with Q-learning is that the temporal difference error is calculated as such. It's the reward, and that is a must. You never, everybody share the reward, minus the Q value for the state action in the past, that is a must. Then in between, you do not have the Q value for the state action ST plus 1, AT plus 1, which is SARSA, which it means I've looked at only one trajectory. It does not have argmax over A Q of ST plus 1 A. It does not mean I'm not hypothetically doing the best thing I'm doing, which is what Q-learning is doing, but actually is doing. I know that since I will follow my policy, and I know that my policy epsilon, I know exactly what are the probability of doing that, I'm summing of over the policy, over the action, the probability of doing that action following the policy I'm actually following, which is an epsilon greedy policy, and the Q value of being the new state and doing that action. So SARSA has one trajectory, one new action, and it does that. And it does that both in real world, so it does do it as a trajectory, and it does as an update. Q-learning as a trajectory with one action, with one policy, but it actually does not care that what action it is. It does the update with the best action it could do. And SARSA does a bit of both and says, I'm a new action, I'm taking all the possible action I could take with the probability of taking them given my policy. Okay, and this is what is done here. So it's average. This is why it's expected SARSA, because it's expected value. It's the average value of the Q of new state any action given by probability of taking that action given the state. Okay. Again, how it done the update once you have this number, same as before. Okay. So this new class, expected SARSA T control, it's the same as all other classes. First, it does this initialization. And then the only part which is different is this. If the episode is done, I have reward plus 0 minus self Q values of the pair state action. But if the episode is not done, I'm doing R plus discounted the inner product, so sum of action of the product, the Q value for all the actions in that state, the policy for all that action in that state. Okay. Now, the only thing which is a bit different is that not only I need to have a get action epsilon greedy, which returns one action with the probability given by the epsilon greedy, but I need to have a function which returns the actual probabilities. Okay, I could have done that here since I already calculate them as a no, it's not true. I needed them. So what I do with function policy is take the current Q values evaluator, and it does the probability the policy in that state given the evaluator. What it does is, first of all, I know that with probability of epsilon, I will have a flat probability. So I first of all I take an array of ones. I divide it by the action size. So this is a flat probability with up to 1, and I multiply by epsilon. So this is a small epsilon probability which is completely flat. And then, as again, I'm taking the best value. I'm taking the best action. Let's say I have 2 equivalent actions. Those actions will be divided by 2. So I will have 0, half, 0, half. I multiply them by 1 minus epsilon. Okay. And I sum both. So I sum this small uniform probability epsilon with some peaks of 1 minus epsilon divided by how many good best choices I have. And this is my overall probability distribution, considering everything. This is my probability distribution of the policy, which I can calculate given the state and given epsilon, and which goes here. So this is truly the expected value, given that I am a new state, and I know the Q values for the state action, and I know the probability of being in that state and doing that action, given that epsilon. Okay, you see, essentially the same as before, but now we have three different ways of seeing. SARSA, trajectory, I'm following a trajectory, I know what I did, I'm going to do the update with what I did. Q-learning, I'm following a trajectory, I don't care what I did, I know what would have been the best thing to do there, I'm considering that for the update. And expected SARSA, I have a trajectory only one because I'm only a robot, I have so many artificial hands. But I know that if I were there, I could have done this many actions with this probability, so I'm averaging out for my update of the Q value. How do they perform one through each other? In this particular case, not that differently, I apologize. But so we have an expected SARSA control. I'm doing 2000 episodes. I'm creating this class. I'm taking the epsilon as before. I'm taking note of the performance. I'm doing the run of the raw episode. Everything is the same. Actually, everything is the same as in Q-learning because I do not need even the A prime, because the single update requires only state, action, reward, new state. What I require more is the epsilon. Why? Because in an update, I need to create my policy. And to create my policy, I need to know what epsilon is. Okay. Then I run it. Wait, I have to run everything before. Okay. Hopefully it not take too much. Okay, again, so this right now is something which is in between the two, so should have less, should be on policy and should have less variance than a SARSA, because of SARSA you have only one trajectory, you have to wait to accumulate all the possible trajectory. Here you like, you know what, I know what the expected value of where I would go is, I use that. Again, however, you see the actual value perhaps is a bit better than the performance than SARSA, but it's basically the same. And you can also see that it does not reach the same height of Q-learning. So again, this has learned a suboptimal value. Has the same problem of SARSA in the sense that it's on policy, in the sense that it's actually using for every update the policy is following. Good. So far we have learned control in the most basic case for tabular systems in with temporal difference in model 3. So
I just
yes,
add a comment. So on the book of Sutton and Barta, you actually see examples worked out where you can appreciate the performance of expected SARSA, which is better than SARSA, especially with respect to the learning rate alpha, which is something that has not been changed here. So for reference on the advantages of expected SARSA over SARSA, you are referred to the book. Thank you. Guess you're muted.
Yes, I will say that I can hear it. I think this is what you were.
Yeah, exactly.
So this is alpha. It's the learning rate, and you can say that. So with alpha is very small. They are rather similar in performance. With alpha very large, SARSA is rather thrown off, and expected SARSA is actually much better. So this was, I think, was the the point. So they're not, perhaps I did not say that well, but yeah, they're not perfectly equivalent, of course. It's just that in this particular case, it's not easy to spot the difference. Okay, last thing I want to deal in a very basic thing. You can read it in two ways. Either I was lazy in preparing the lecture, or I wanted to give you many exercises to do home. I want to briefly touch on the problem of convergence. So far, we used two constant values. We used constant learning rate alpha, which is bad, it's bad for a very simple reason, because the values will not converge, which is not something we want. And instead they will oscillate forever around it. You can also see it here. I mean, it took 250 episodes to obtain basically the same performance. You will, it stays the same for 2000 episodes. Okay, so it means that after a while this is not perfectly. I mean, the convergence, this could be related actually to epsilon, but it doesn't matter. It means that still the convergence is not that great. On the other hand, we know a solution. The solution would be to implement some alpha such that the sum of the squared converges and the sum diverges. The problem is that this is a mathematical limit to infinity, and limit to infinity have the problem of being to infinity. So generally speaking, you have to find a balance between having something which yes, it's true that it converges, but should not converge too fast, and but at the same time should not diverge. So I mean, you have to find a balance. Some way of doing that, which is not the best. It's something which I just suggest, and it's done sometimes. Is that you could use a constant alpha up to some point t, and then use some function which go something like that, in the sense that they decrease with some power of the time, but they are constant up to some point t star, and then start to decrease. And also they start to decrease, but the rate which we start to decrease, it's tunable by this k. Okay, this just means that it is true that this is a proof. It's proven fact. But if you take any, sometimes it's called the learning rate schedules. Or scheduler, if you take any scheduler and you try to make it converge in your lifetime, sometimes it does not work. Second thing, epsilon greedy policies are bad because you are doing suboptimal things, and we have seen with our own eyes with SARSA, it learns actually the wrong path, the wrong shortest path between start and end. Again, you have seen in class, one of the possibilities just that the epsilon goes down with time. One other which Antonio was referring to, which is it's a more interesting part, is that you can take count of every time you have visited the state action pair. In this case, it would be feasible because now I just entering, when I do the episode, I just enter a new count array of dimension state space action, which is rather small. It's 4, 12, 4 again. And then I do a +1 every time I do in that particular couple SA. Then I have a number which indicates how often I visited that particularly couple state action. And then it means that if I have not visited, I want to be as exploring as possible because I'm entering a new room. Perhaps I want to know what I'm going to find out. But if it is, it's the same as I mean, you can open your own fridge many times, but it will not change what it is. But if you want to find something in a supermarket, every fridge is a new story. Okay, this is basically what it means. how many times you're doing exactly the same thing, and epsilon, so the probability of doing random things, diminish by the number of you visited that particularly couple. You can clearly see what is the problem. If you have a state space and action space which is huge, then you will have visited so few times everything that this approach becomes not great. But then again, maybe any approach will, in that case, maybe any approach is not perfect. Okay, again, I have, I'm proposing, because this is something which I use more or less, yes, which I'm using below, some kind of formula, which is just this here. So it decay after a time t star with a power slightly larger than 1. Okay, let's do it. Same as before. I'm doing, but now I'm first of all initializing an epsilon, which was the epsilon from the start, which will be the one starting and then decaying, and a learning rate from the start. And then I'm initializing the expected SARSA class with the learning rate 0, but at every, and I'm adding a t star, so a time for my point decay to start, and I'm adding a count. And during the run, I'm just adding 1 every time I do a step. So every single step counts 1. And then when the step has succeeded t star, I'm changing the value, which is the internal variable of the class expected SARSA, to this value, the original value divided by 1 plus 0.003 to the power 0.75. Epsilon does the same. Epsilon is given then to the expected SARSA. So effectively, we will see the results for both learning rate and epsilon, which decay with this kind of powers after a certain decay time. What we see after a couple of seconds of staring to a blank screen, okay, perfect. We have again our usual values. Here the value say please do not go down. The value see okay, you can go up, but it's not perfectly sensible thing. This generally speaking a good idea, and going left it's not a good idea. And then what you see is that this is Q learning and expected SARSA performance during the simulation. You see that after some learning, in which the performance for each episode goes from -40, so rather a long trip, to the best value, and then it stays on the best value, and then sometimes still does different things, because hopefully our epsilon is not so small that it will never do anything strange, because the sum, again, the sum of alpha should diverge. So eventually, by pure numbers, something strange should happen. So this is why at least once it does crazy things. And then, but most of the times, it's the perfect thing. So it should have converged, even if t did not go to infinite. And we can see, perhaps, that this is the best. Yes.
Is the comparison done with Q learning with fixed epsilon and alpha?
Yes. Sorry. I just took one which I already knew. So Q learning. This is what happens with Q learning without with epsilon is not decaying. So this was the old Q learning. Okay, this was constant epsilon, constant learning rate blue, which does find the best optimal thing, but it's following a policy which is rather poor because it has a large epsilon, followed by SARSA, expected SARSA with learning rate and epsilon going to 0, which means that it has actually converged both in values, should have converged both in values and in policy. And you can see, for example, here, that it does find the optimal policy, which expected SARSA with constant epsilon of 0.05 did not find the optimal policy. So now it has, and also at least for the points which are following the main road, which is like the optimal trajectory, the values are very similar to what we expect. So it's 0 here, -1 here, because you are taking, it takes one action to go to the end, 2, 3, 4, 5.01, because it still has not perfectly converged, but still it's much better convergence. 6, 0, 1, 7, 8, 9, 10, 11, 12, 13. So the Q values have converged much better than, for example, let's see, let's take Q, perhaps also Q learning was not bad. Q learning was, you see, Q learning was 0, 1, 2, 5, 6, 7, 8, 7, 8, 9, 12, 13, 14, 13. Okay, he had still some misgiving. This was Q learning, which learned the optimal value, but still it was rather fluctuating in the Q value. Now, learning rate going to 0, epsilon going to 0. Effectively, this has converged both in policy and in Q values. Okay, with this, we have the basic structure of what it means to do TD control for model-free systems in a tabular case, which is a very basic thing, but it still we have dealt with unknown models. What I mean by unknown models, I mean that these incredibly stupid algorithms which we have here, and I mean like the code, the class, if instead of having this, I said also the last time, instead of having where did I define that? Somewhere I defined the environment to be grid world environment, right? But possibly 2 hours ago. If there, instead of saying, you know what, this is the environment is a grid world, I will, yes, here. If here, instead of having environment is equal to e grid world something, the environment was anything which has the same basic structure of you can ask for, you can ask to do a step when you do an action, and you get new state, new reward, done, and etc. etc. This should work in the same way. This is an algorithm which does not require any information of the model. It requires only information on the trajectories. And of course, it works only if the system is tabular, in the sense that there's a discrete action space, a discrete state space. But there is nothing specifically tuned to the fact that this is the grid world with a cliff, and maybe it will not work if the grid world was working other. No, if you have trajectories, then you put them into the algorithm and it will work. Perhaps it's too simple to achieve convergence, but I mean, it should work. This is what model-free means. Okay, do you have questions?
Can I make a question on the last plot?
Sure. Wait. The last plot was, you mean this or this?
No, the next one.
This one?
Yes.
Yes.
Why, for example, in the upper left part, there are some actions that are that seems strange that goes up?
Okay. Again, the problem will be again a problem of convergence. So this, let's say, look at the best trajectory possible. The best trajectory possible is go up and then all the way right. Okay. So and then let's think of a trajectory which actually goes to the top left corner. First of all, you have to go up, which is what you will do. So even if an epsilon goes 0, you will eventually go there. Then the greedy action says to go right. Do you want to go up? Okay, you will have to wait an epsilon probability action to go up. Okay, maybe you're going to do it. Okay, with probability epsilon, you are going there. Then the epsilon greedy probability is saying that you have to go right. If you want to go up, you have again to wait for a chance, epsilon probability chance to go up. Okay, and then when you arrive there, you will do something and you will have a very small amount of information on what you've done. Okay, what this means, it's that the frequency of update in this top left corner will be much smaller than anything anywhere else. So perhaps for the information it has achieved in this top left corner, which may be very few times of exploration, the Q value of going up, it's actually the best. It's actually the best in all four. Okay, and essentially, in a sense, it's not that surprising. I mean, going up, it's not even. I mean, you could do 4 actions, and actually going right is clearly the best. Perhaps going down, but going left and going up, it just wasting 1 turn because you're actually staying together. So it founds an action which is wrong. It's not optimal, but it's not even that wrong. It's not falling off of a cliff. And of course, it's an action which has visited perhaps so few times, which has not yet converged to the true value. Again, if you wait infinite time, you will be you can go to Professor Celani and say, look, I waited infinite time, this still is the wrong action, and then he will be the theorem will be wrong. Okay, but and again, the suggestion from Antonio was perfect. If you calculate the number of or the frequency it has visited those states and done those actions, you will probably see that those parts there are absolutely not visited so much, the least visited of all.
So once we reach the top left corner, we try to explore more, and this section is given because we didn't reach the top left corner enough times to say which is the best action to pick. Okay, thanks.
My current intuition of that is yes. Then there could be problems with the code and everything, but I see it. I do not think it's strange, and I think it's exactly that for that reason. We have not reached that top left corner sufficiently many times so that it has converged and he knows that there is actually a better action to do.
Okay, thanks.
Okay, may I come in here and say things? So the first thing is that I accept your challenge. So if anyone finds out that there is a trouble, I'm happy to discuss. And second thing, and here you must have been discovering the pattern already. So every question comes with an exercise. So one way to get around this problem is rather than starting all the times, all episodes from the lower bottom corner, you can start from random places in your grid. And therefore, you can start sometimes also from a top left corner. In that case, these random restarts allow you to explore in a forced way. And therefore, your convergence to number of visits will be much better in that case. Do you agree, Emanuele? Good. I'm done here.
Can I ask So in the SARSA, the policy is given. So it's like you imply that in the environment, you already know the policy and we cannot do anything about it. But in the Q learning, it's like you are switching between policies because you don't know what is the policy.
Let me clarify. Thanks for the question. Let me clarify something. In SARSA, the policy is not known. You can see in the code, or you can see it in the pseudocode. It's the same. The policy is a function of that queue you have in that moment. So, for example, here you see this epsilon greedy. So when I am at certain time t, depends on the Q value I have in that moment there. So the policy is not fixed from beginning. It's not fixed from the start. At the beginning, the Q value have some values. I start with 0, but they could be random, and the policy will be strange. Then as the time goes on, the policy is always different, but always following this formula here. So the policy adapts to the Q value. Okay. So it's not fixed if it was fixed from the beginning to the end, then it would not be control. It could not learn to do the optimal policy, but it changes not in a strange way. It changes following always the same formula, which is look at the Q values, which you accumulate and change and store all the time. And from those Q values, create the epsilon greedy policy. Okay. So both things change from step to step. The Q value in the pseudocode, the Q value changes because you have visited new state and you have this formula here which give, okay, my Q value, I thought it was 2, now it's 2 plus 2.01. Okay, this is the changing Q values. But since the Q value has changed, also the policy, which is constructed on the Q value, has changed. So in SARSA, both Q value and policy change together all the time. So it's not fixed from the beginning to the end. Perhaps I made it sound that it was fixed. What is fixed is how you get the policy from the Q values. Okay, when you have a Q value, you get the policy in this way here. But since these Q values here change all the time, also the policy changes all the time. Okay, this is one thing which I hope it's clear. If this is clear, perhaps I have also another distinction which I wanted to do in even more clear. So is it clear, this thing? So that it's not a fixed policy, but the policy changes because the values, Q values changes. Is it clear? I hope so, a bit. So the second thing is what is different between SARSA and Q-learning is that in SARSA, you have that the policy, the Q value changes because this changes all the time. The policy changes with the Q values, and the policy is used both for making the trajectories and both for making the update. Okay, so you have Q values change. Q values make the policy change. The policy create the trajectory change the Q value. Q value change the policy. Policy make the trajectory make the Q value. And this is go on and go forward. This is SARSA, which is because called the on policy system, because it has the same policy to make the trajectory and to evaluate. Q-learning has exactly the same thing, but with a small twist. So yes, the Q values change in time. The policy which are used for a trajectory, which are the same as in SARSA, change in time because they are a function of Q values. So again, you do not have a fixed policy. You're changing everything, but then the policy constructs the trajectory, but the update is not done using exactly the trajectory. It's done using a bit of a trajectory where I was and where I got, and a bit of extrapolation in the sense that instead of doing the action I really took, I will use for the update the best action I could take. Okay, but still you started with zero knowledge on Q values, and the policy was the worst policy ever. And as time accumulates information, the Q values get better, and the policy which you are following changes. So again, it's not fixed in time. Was this clearer?
Yeah. So there should be there will be a time that the trajectory of SARSA and Q learning will be the same.
Yes. If you change epsilon to go smaller and smaller and smaller and smaller, and the learning rate goes smaller and smaller and smaller, so you are in the condition to reach convergence, the optimal policy for one and the optimal policy for the other, since they are the optimal policy, which is the property of a system and not of the method, should converge to the same. And you can see it now. It's not super easy, but again, this is how can I do it? Wait, apri immaginato scheda. Okay, this was Q learning. This was expected SARSA with, okay. Oh, I hate you.
Yeah, may I add one thing while you search for the file?
Yes, sure.
So grid world is a bit tricky in this respect because as the trajectories walk in right angles, there might be more than one trajectory that is optimal. So it depends on whether you take the turn first and then go down, or you take a turn, you go down and then you go left. So from the same point, there might be more than one optimal path. And this is reflected in what you observe as well. So one has to be a little bit careful when there is a degeneracy of optimal paths that connect your start point to the end point, which happens if you are not starting from the lower bottom square, but if you start from any other point up.
Yes, something which one could do as an exercise, if I want to follow Antonio's example to make every question an exercise. Now, as I pointed out in my code now, to calculate the greedy function, the greedy policy, which is what plotted here, I'm taking the best action with an argmax, which means that even if there were ties, I chose only one. But you can actually try to go to convergence and select ties and plot both actions together. And you would see that perhaps here it looks like slightly different policies. They would be much closer policy, because again, as Antonio was pointing out, if you are anywhere not on the cliff, if you go right or if you go down, should be exactly the same, because you are in both cases going closer one to the endpoint. So there should be a tie. But in my code right now does not in a tie for the greedy policy does not show both of them. But you can see that they have converged at least in most of the states, and in all of the states composing the optimal trajectory from top down, bottom left to bottom right, they have converged to exactly the same policy. Okay. This here and this here. Are there more questions? It's a bit late, so if you have, please do. But otherwise, yes.
So in the expected SARSA, the spectrum of policies is also.
Tell me again, sorry, in where?
Huh? In the expected SARSA, you have to have a spectrum of policies.
In the spectrum of policy, what do you mean by that?
Because in the SARSA, the policy is just how to update Q.
Oh, wait, by policy, I refer to the action to take given a certain state. So to me, the policy are the arrows here. It means that if I am in this position, the policy is the probability of taking that action right instead of taking the action left. So here what I show is the optimal policy as converged for the two cases, expected SARSA on the left and Q learning on the right, which means that I'm showing the action to take if you are in a state. If you, by a policy, you mean what you do to change the update. I don't think it's generally called a policy. And the only difference between Q-learning and SARSA is in how you define the delta Q, so this update of a Q value. But the values should converge. So the values for the Q of the couple state action in every state for each action with convergence criteria and with infinite time, they will converge to the same numbers. Again, the values, as you've seen here, you can see the second plot from up. You can see that they are actually not that far off, in the sense that if you arrive to the end, you can see that there is a 0, and it's 0 in both cases. Then there is a 1, which is good because it means that it takes only one action to go there, which is probably 1. Then it's a 2 if you are at distance 2. Then there is something close to 3 in most of the places which are distance 3. So again, it's not at convergence yet, but the two methods will converge with probability 1 if given enough time with decaying alpha and decay epsilon to the same values. They have not converged yet because of finite time and etc. etc. Was this in any way part of an answer to your question? I take it as a almost no, but perhaps if you have, if you want to continue, please write to me and any of you. I will try to answer to mail, Slack, and everything as quickly as possible. And sometimes it's very useful if you do specific question, also broad question for me, in the sense that I know what I completely was of point of speaking, and for you, because perhaps you do not need to spend 2 hours releasing an election, and I will answer in 2 minutes, and maybe it will be clearer with a one-to-one comment. So we went late, so I apologize to everybody. As always, if you have questions, write, ask, and everything. And thank you very much. I will stop recording. I perhaps should have done it before.